BCGs. So there's a really nice paper that came out by a graduate student just this last couple of months, where he shows for a whole range of masses, okay, the metallicity gradients. Our sample is inside of this red high mass bin, right? So their bin isn't only BCGs. What we're going to do is filter out just the BCGs and take a look at all of the properties. And our sample with manga is going to be a little bit higher redshift, like 0.1 instead of 0.05. What they found is, looking beyond one effective radius, they found a flattening in the metallicity profile, which in their Toya model suggests the inside of the large galaxies is built in situ and the outside is built ex situ, so through mergers. I expect we'll probably find the same thing for BCGs, but it'd be nice to check. So that's where we are going with this, and it has been a real pleasure to be here. I've been looking forward to this. It's nice to see so many friendly faces. Thank you very much for having me.
Okay, I'm gonna get in there first, because okay, so my question is, it's related to this last point. So for massive galaxies, we think there's like a two-phase formation scenario, same as you were talking about. The center forms first, and then the outskirts form through giant merging. So if it seems like, and that's just all called part of the elliptical galaxy, and there is a break in, well, a gradient in properties, as Charlie has shown. So is it just a question of semantics, that it's ICL versus BCG versus for the massive ellipticals, it's just inner core versus the outskirts?
So Bender talks about this in his 2015 paper, where they look at they look for photometric breaks in the light profile, and also for breaks in things like metallicity and age, and then kinematic breaks for A delta 2199. And actually this Nucluge paper also goes into, like, they fit, they put single and double devocular profiles to all of their things. And it's true that photometrically you can find often a huge subset of BCGs that have double profiles, but the double profiles are usually fitting the inside of the galaxy and the outskirts of the galaxy, not the ICL. So a lot of work suggests that it's very difficult to see the ICL in a photometrically. I think a nice way to do it, a really nice way to find the difference is kinematically with the velocity dispersion radial profiles, which is what we're going to be mostly interested in here. Again, this flattening out, that's not just for BCGs. So who knows, they haven't looked at just BCGs, but the idea is that this is for massive galaxies. You even see it in the second mass bin as well a little bit. BCGs would then maybe look a little bit different. Maybe this would be more extended, maybe it would be somehow different. Or maybe it wouldn't be, and that's not a good way to identify the ICL. But you're right, this flattening is not for BCGs. It's for massive galaxies in general.
Former student here, Ben Cook, was looking at simulation and found a nice correlation between the metallicity gradient and the light profile shape.
Okay.
Have you looked at, with your data, comparing the spectroscopic parameters with the light profile?
This is kind of like a little bit what we were just talking about, right? Is that there's some contention as to whether or not you can do this with looking at the light profile. The new paper with the 100 are saying the light profile isn't, they can't find anything, but they're not hooking it directly with metallicity because they can't do that. So we haven't done that. We haven't fit profile. We actually started to fit with GIM2D some of the galaxy profiles, but we didn't finish that. No, this stuff is arguing purely on a difference in a dramatic drop in age and the difference in velocity dispersion that we can find the change where the ICL comes into play. Okay.
Yeah, so I don't want to hammer away on this nomenclature thing because I agree. I think it's sort of dangerous. And I don't know what it means to be in the ICL, but I think something that is meaningful is the words that appear on your last slide, which are in situ and ex situ, right? Because that's actually a well-defined physical thing. So I had the feeling that's sort of what you were trying to get at was this ICL versus BCG distinction.
That's right.
Okay, good.
Yes.
So if that's correct, then there was a grad student here called Vicente Rodriguez-Gomez who looked at this in great detail in simulations.
Oh, okay. In the lustrous simulation?
In the lustrous,
Yeah.
yeah. And I think there are a lot of plots in his papers that explain a lot of the things.
With the age and metallicity and everything?
Yeah, I can't remember exactly every quantity of that, but basically there is a radius, which is not too far from the
Yeah.
radii you were considering, where you essentially transition smoothly, though, so no
Okay.
sharp break, but
Yeah.
smoothly you transition from in situ to ex situ.
Right, okay,
And
yeah.
that would then, I think, just sort of very
Yeah.
generically give you the.
Yeah, can you give me the name again?
Vicente Rodriguez Gomez, but I can send you the.
Oh, yes, that'd be wonderful. Yeah, thank you.
So if your hypothesis is that the origin of the ICL is galaxies which were destroyed instead of sun, shouldn't you find a correlation between the properties of the ICL and how dense that region is in terms of number density of neighboring galaxies? Like the distance
Right.
to the next galaxy?
Oh, yeah, next to your neighbor or something. Yeah, that would be a nice way to do it. Yeah, the way that we show that is to look at the, like, the velocity dispersion of the cluster. So we think about the potential well of the cluster being parameterized by the velocity dispersion of the cluster, right? But yes, there's probably a great number of ways to do that, and that's a great one. We should totally look into that.
Just another short question. What about the metallicity of the ICM gas there? What is you must have, that must have been measured for some of these.
In the X-ray?
In X-ray.
Yeah, well, I know there's a lot of measurements, like, right in the core of the
Right.
cluster,
Yeah,
right?
that's
Yeah.
asking,
Yeah. No, that's a good idea too. We could look at, like, to see if the metallicities are correlated. It's a great idea. Yeah. There's so much to do in this data set. It's very exciting. Yes.
Yeah, we have X-ray metallicities for basically a huge fraction of the sample from Chandra, but we only do the core, right?
Yeah.
So it's only going out to about where SparsePak,
Right.
7 arcseconds. or
Okay. Yeah. So that'd
basically
be.
the ICM metallicities are like uniformly like 0.4.
Oh, there's no. Oh yeah. Right.
Not always, but like.
Yeah. Okay.
It's
Yeah.
either for clue cores or it's non-clue cores.
Oh right. Okay. So they would be quite different than what we're
And
seeing.
also like metallicities and X-rays are hard.
Yeah. And again, these, anytime you see like age, metallicity, like we used a certain set of stellar models using a certain fitting program. So I'm not trying to say like the metallicity is 0.4, right? But when we explore a little bit, the metallicities are always very, very high in the center, right? And compared to the outskirts, using the same method, they're higher. Yes.
I'm just wondering, getting at this question of the difference between the BCG and the ICL, do you have any in your sample where the BCG is offset from the cluster center? Does that
We
really
do.
increase?
Yeah, we have there's 4 or 5 of them that have really high offsets. So this is the distance between the BCG and the X-ray peak, okay, log. So we have some that are like 100 kiloparsecs away. And actually thought going in that maybe like all of the ones with a velocity dispersion that doesn't increase to the core value might be far away, right? Because they're not sitting in the middle of that cluster potential, in which I would expect decreasing slopes, and I would expect these guys to all be down here, and they aren't.
One more question for Brian, and then last question to you, buddy.
Great. So there was a recent result showing that the stellar halos of galaxies around one of the galaxies, like the Milky Way or nearby galaxies, where you can actually resolve stellar populations.
Right.
It's shown that those stellar halos are built in simulations. They're built by the largest largest merger that happens in that galaxy. That giving you this indication that if the largest merger was a red and dead galaxy or a very rich galaxy, you can tell what kind of thing merged with that galaxy. Is that the same kind? Could that possibly be the same kind of thing for BCGs, where the ICL, which is your stellar halo, might give indications of the merger history of galaxies, so that differences in the metallicities of the ICL can give you an indication of what merge with that central galaxy.
Yeah, that's what we're hoping, you know, is something powerful, hopefully, that can happen from this data, right? Is that, just looking for, this is always one of them, isn't it? One more. Is that in looking at the metallicity separately of the ICL from the main part of the galaxy, right? That we can say something about the stars that formed those two different regions, right? That's what you're getting at? Yeah, and so like, for example, there's a few of the models, simulations that look at ICL growth, find different, really drastically different things. So some models predict that this is the fraction of stars in the cluster that are ICL stars. And this is the galaxy mass that formed those stars, okay? The mass of the galaxy that the stars ripped off from. And in these models here, which are the Morante models, most of the ICL comes from these large red galaxies, 10 to the 12 solar mass galaxies. But in other models, okay, where the ICL instead is ripped off, from like L star galaxies, 10 to the 10 solar mass galaxies. So with our so looking at the metallicities in our sample, in the different regions of our sample, we can use like the mass metallicity relationship and kind of infer what mass galaxies the stars came from. And it looks like, you know, like our ICL stars, halo stars, our ICL stars, the stellar populations are much more in line with L star galaxies than they are with large red galaxies.
Is that for all of the galaxies in your sample, or are there differences that might say that one
I'm
galaxy
gonna,
might be merged with
would
all-star
it be
versus-
okay if we continue?
Oh, yeah.
Yes.